To start this one?
Yeah.
Come here, so you go.
Right 0. That's how I did it.
Okay, so this is equal to the limit as x goes to infinity of e to the x over
That was funny.
e to the x squared. Is that correct?
Yeah.
Now the thing is, you have to be really careful. Is e to the x squared equal to e to the x times e to the x?
No.
No. E to the x times e to the x is e to the 2x. You add powers when you multiply them and they have the same base. You add powers when you multiply them when they have the same base. So what this is equal to, this is the limit as x goes to infinity of e to the x over, is there any way to rewrite the bottom? So for example, is it equal to this? Is this correct?
No.
No, it's not. That's exactly what I just said. You can't do that. You absolutely can't do that.
It'd be 2x. It'd be 2x.
What would it be? Yeah, because you'd multiply. If I wrote that, it would be 2x. You're correct. If I wrote that, it would be 2x. Absolutely. Is there? So, but my question is: there any way to rewrite this?
No.
2e, like 2e to the x power?
Well, not really. How do you bring the 2 down?
I just thought I remembered.
Yeah, well, you did. What you're remembering is the natural log. The log of a to the x is equal to x ln a. Like you can do that, but we have no natural logs in here, right? You don't have that. You don't have it. So this kind of gets to.
This is a horizontal because there's the degree and then.
Yeah, but this is not. Neither of these is a polynomial.
Oh.
Neither of these is a polynomial. That being said, you're starting with the same base, e on the top and e on the bottom, right? Which one is going to get bigger much faster, x or x squared? X squared. No, you can't. X over x. No, it's not the same. No, it's not. It's not. So what I mean by that is you can use logic, and in this class that's okay at this point because we haven't been given all the tools possible. But here's the thing: which gets bigger much faster, x or x squared? The denominator gets bigger much faster. So this actually goes to 0 because the denominator is what's the horizontal asymptote here? Y equals 0. But it's not asking for the horizontal asymptote. It was just asking for what the limit is, which is indeed the same thing in this case. But the point is, you're raising the same number to a power, e to the x and e to the x squared. Which is going to get bigger much faster? E to the x squared is going to get bigger much faster. So you're looking at a small number over an enormous number. So what is that going to be getting infinitely close to? 0. That's it. Moving on. So you're going to end up with 1 over x minus 1 plus 1 over
X minus 1 times. I mean, x minus 2 times x minus 1.
x minus 2, right? So to add or subtract fractions, you need a common denominator. So what are you going to...
X minus 2 on that side.
x minus 2, right? So you end up with the limit as x goes to 1 of x minus 2 minus 1 all over what? Minus 1, x minus 2. What does the numerator simplify to? You end up with the limit as x goes to 1 of x minus...
No. Wait,
No?
you wrote something wrong.
Did I write something wrong?
Yeah, it's plus.
Oh, it's plus. Thank you. That would actually make it that wouldn't get us anywhere fun. So you get x minus 1 over x minus 1, x minus 2. What cancels? And that's exactly what we're aiming to cancel because now we end up with the limit as x goes to 1. It's 1, right? Is it the limit? Yeah. Of 1 over what?
X minus 2.
Which is just going to be what? Negative 1. Exactly. Factor, add them together, cancel, done. I need to check something. 1 second. Are we okay with that?
Yeah.
Yeah. X squared over x squared is 1. 4x over x squared is 4 over x. And 1 over x squared is 1 over x squared. Now, but here's the thing. Now you can look at each of these things, and you know conclusively, because I told you yesterday, this has to go to 0. This goes to
0.
This goes to 0. So this ends up being 4 over the square root of 1 plus 1, which is 2, which equals 2. And you're done. There it is. There it is. Time. And this is going to be position, sure. In terms of time. Usually, and I don't know why, usually you see position as s of t, and this is as t. I don't know why it's s. It might be some Latin word, but velocity is v of t and acceleration is a of t, so I don't really know. But just deal with it. There's no point in arguing with it because it just is. So if this represents, we're going to say position as distance from the origin as time goes on. So, for example, this particle, let's say it did this. Let's say that was the position. Let's make it a little better. Let's make it like this. So what's going on here? The the particle is moving away from the origin and then moves towards the origin and then it levels off. So if this is the position, let's say I was looking at this specific point, let's say right here. Let's say we're looking at that specific point. If I gave you a function that modeled this curve, and then if I gave you a function that modeled that curve and told you like what this x value was, let's say x equals a, could you find this slope? Sure. How? What methods do you have? What?
You would take the.
You're finding a slope of a tangent line, so what do?
Say 2
on
points.
either side.
Yeah.
I'm going to take 2 points on either side, or what have we been doing repeatedly for the past week?
Arbitrary.
Limits.
You would use a limit. Okay, exactly. So you would look at what kind of limit. What limit would you look at? What trail? What have you been using? What's one method you've been using? You've been using your calculator in what methods, for example? What's one way you've been using your calculator? You've been making a table, right? And you're making a table of what values? A table specifically of what values?
X and 1.
No. You're making a table of what values when you're trying to find the slope of a tangent line. What have you been doing? Okay, I got to pause this before I actually flip it. What have we been doing? We've been taking which point and doing what with it? We have 2 points labeled there, so which point are we doing or doing something with? This point is anchored, so which point is moving?
The
X, f of x, and we've been measuring the slope of the secant line, and then what do we do with the point? We get closer and closer and closer and closer, correct? And we keep on measuring the slopes. We have 2 points. What's the slope between those 2 points?
F of A.
F of A.
You got it.
F of x over what?
Over A minus.
Over a minus x. Over a minus x, exactly. What's another way to write that same exact thing?
Change Y.
Change Y. Yeah.
You could write that as change in y over change in x. What's another way to write it?
Y1 minus Y2.
Sure, okay, that's fine. Minus y2 over x1 minus x2. But what I'm trying to get, and you're doing a great job of coming up with alternatives, f of x minus f of a over x minus a, for example, right?
Yeah.
Correct? So what have we been doing? Which one is anchored, everybody? Which one was anchored?
F of A.
The a is anchored and this is anchored, right? What's changing? The f of x isn't changing. The f of x is changing because what's changing? X is changing, exactly. X is changing. What is x doing?
It's getting
Getting closer to A.
X is getting infinitely, arbitrarily close to a. So you have this right here. What does this represent right here? So you can say that the limit as x goes to a of f of x minus f of a over x minus a is equal to what on this graph? Is equal to what? Is equal to what? M. It's equal to m. The slope of the tangent line at what? At what? A, comma, f of a, correct. That represents the slope of the tangent line at a, f of a. If you have a point and a slope, what can you therefore construct, for example? What's one thing you could construct if you have a point and a slope? Equation of the line, right. The equation of the line, exactly, right. Exactly. So this would be the limit definition for the instantaneous rate of change at the point a, f of a. If this was a position function right here, what would this m represent?
The direction of that molecule.
Nope.
Instantaneous flow.
Correct, kind of. I'm sorry, I wasn't totally wrong, but it is the instantaneous rate of change of what? Nope. Nope. Of position. What is instantaneous rate of change of position? That's also known as velocity. So instantaneous, if you're calculating the instantaneous rate of change of position, you end up with velocity. So for example, this particle is moving away. What can you tell me about this velocity based on this rough sketch? What could you tell me about that velocity? What's one concrete thing you could tell me? Yes. It's positive. It's moving away from the origin, right? That's the only concrete thing you can tell me right here. It's the only concrete thing you can tell me. We have no function right there. We have no function. I haven't given you an actual function. Just break that rule, right? So let's do one concrete question. What could I theoretically ask you for? Let's make a nice easy one. F of x is equal to x squared. Well, give me 1 point that's on there. Something more. 3, 9. I like 3, 9 better, right? Okay. Let's say at the point 3, 9. I could ask you, what is the equation of the tangent line through that point? What is the equation of the tangent line through that point? We have a point. What's the only other thing we need to write an equation of a line? Or slope. That's what we're aiming for. That's correct. You could use another point, but we don't have one, so we need to find one or find the slope. That's what we're going to do here, correct? So what are we going to do? We're going to use this limit definition. We need m. M is going to be the limit as x goes to a. What is our a value this time? 3 of f of x, right? What is f of x? Well, we'll write it as f of x minus f of a, but what's a this time? A is f of 3. I'm going to write out a few steps so you can see where it comes from. Over x minus 3, because that's what a is, correct? So what do we have here? We have the limit as x goes to 3 of what? Of x squared minus 9 over what? Can we solve that limit pretty easily? Yes. So the top is the difference of x plus 3 times, and we're going to end up with over 3. It cancels, so it's equal to the limit as, as x goes to 3 of x plus 3, which is 6. So that's the slope of the tangent line. So could someone tell me really easily and quickly what the equation for the line is? Raise your hand and tell me what it is. Just rattle it off. So that's the slope, and this is the point. What is the equation of the line? Someone raise their hand and tell me here. Go.
Y minus 9 equals 6 x minus 3.
Yes, done. Stop there. Don't go any further. That right there is a totally valid, 100% correct way of writing the equation of that line. If I don't say specifically a form, stop there. If I said slope-intercept form, are you done? No. What form is that? Nope. It's point-slope form. Use that. Unless you're specifically told otherwise, stop there. Why do you guys tend to feel as though you have to go to slope-intercept form? Because, well, that's just what you use first. That's how you thought about lines, right? Kids these days, right? Kids these days, right? You do not have to do that. You can stop right there. So right there, there's the slope. That is the equation for the line of tangency. So we could check this real quick. Let's check. They're just absolutely not checked. I'll ask a question like, how many movie tickets should Sally buy to optimize her costs, right? And it's like 7 trillion. You're like, I don't think he's asking that. When I taught finance years ago, I had a problem where